Okay. Well, the first admission is that I'm one of those really unfortunate creatures that doesn't have a call sign. So, if I can get away without a lynching, that will be a success this afternoon. Brian Coleman asked if I would be interested in being a bit of an interloper at this conference and talking about radio astronomy, amateur radio astronomy, I should add, with the intention of those of you that clearly have the technical capability to engage in amateur radio astronomy but haven't done so yet might have a dabble at this. I'm really going to go through the main points of my presentation. I don't have time to cover everything, but there are extensive notes accompanying the PowerPoint presentation on the DVD, so you can delve into the detail. It comes in two parts. The first is a little bit about astronomy, and I'm talking about detecting a really quite weak signal from an extragalactic object in the constellation of Virgo, known as Virgo A. And the astronomy bit will cover the location, the nature of this source, which is also known as Messier 87 galaxy, what the expected signal strength is and what the spectrum looks like, so that in the measurement section we can pick a suitable observing frequency, which is obviously related to the antenna type that you want to use, what the receiving system is, and then I'm going to talk a bit about the interferometer, because this is an interferometric observation with transit scans, and then I'll present a result or two and some conclusions and comments. First thing I want to do is really to highlight, there's the Earth, and that's Neptune, and it might seem like a long way away, but actually it's 0.305 light years, which is nothing, absolutely nothing. The nearest star is 4.3 light years away, and I'm going to talk about detecting this external galaxy to the Milky Way, which is actually at 53 million light years. So, a bit of scale. The Milky Way center, the Sun orbits at about 27,000 light years, and we are located in a spur of a main spiral arm. So we just do our thing. We'll come and we'll go. That's where we are in this little spur of a major spiral arm. Now, the Milky Way is in a small group of galaxies, approximately 400,000 light years in diameter, which is called a local group. And you can see if we're there, I think that's Andromeda, M31. And there are a little cluster of galaxies at these distances. A parsec, by the way, is 3.2 light years. And the furthest out galaxy is called Fornax. So I hope you're beginning to get a scale, an idea of scale for the observation that we're intending to make. Now, this local group is located within about 10 million light years diameter. And you can see M31, our nearest spiral galaxy, 2.5 million light years. But that is really only a small part of a cluster of galaxies, which itself is isolated in space. And the thing that we're interested in is off here, the Virgo cluster, which is an even bigger cluster of galaxies. And the measurement that I'm going to talk about is detecting one of the galaxies in that Virgo cluster. So there's our local group, and you can see the other major galaxy clusters here. And the Virgo one is about 53 million light years. But it depends who measures it. They still don't have a very good way of determining the distance to things in astronomy. It's a pretty hit and miss affair, actually. Now, that's the Virgo cluster. You can see, I hope, the projector's not that bright, but I hope you can see there's like 80 or 90 galaxies. And the one we're interested in is M87. That is a 1 degree on the sky. So this is a fairly big patch of sky. I'm going to use an interferometer at 408 megahertz. I'll describe that later. But essentially, if I take the central beam, it is about 1 degree by 30 degrees. And in a transit scan, that 1 degree will just move across the sky as the Earth rotates. We can get a fairly clean record of this celestial object because M87 dominates the radio emission from the whole of the galactic cluster. You can see some other signal levels for various galaxies in that group. But M87 is way above all the others. So we should get a nice, clean interferometric fringe pattern from this source. So let's talk a little bit about what M87 is. It's more than 3 times the size of the Milky Way, and it's one of the most remarkable objects in the sky. It has a huge radio emission, which is produced by an active galactic nucleus and a strange relativistic electron beam jet out of one of its poles. Its coordinates are here. It's only visually about 8 arc-minutes wide. And if we put it on the same scale as the Milky Way, there's the Milky Way, 100,000 light years. And M87 is a giant elliptical galaxy. Elliptical galaxies are usually old and not very interesting. But right smack in the center of this one is a very interesting phenomenon. It's 200 times the mass of the Milky Way, and this jet projects 5,000 light years. And if you remember that the distance to Neptune is 0.305, that's a pretty big object. And it's that produces the radio emission. It is almost certainly powered by a gigantic black hole, almost at the center of this galaxy, that's eating matter and producing this huge radio jet. You can see another picture of it there. You see how it breaks up into striations. So it's not a continuous stream. There are things going on where the black hole feeds for a bit and then stops and then puts out another pulse of radiation. The black hole is estimated to be 6.6 billion solar masses. And it has an accretion disk bigger than the orbit of Pluto. From radio measurements, they find that the black hole is actually not in the mass center of the galaxy. It's actually displaced by about 80 light years. And there are various theories as to why that is. One of them being that it's actually a reaction from the jet, that it's actually pushing the black hole away. Very flaky stuff. Nobody really knows. But the rotation of the black hole produces very strong electric fields, and it also has a circulating magnetic field in the disk. And it produces a radio emission by the synchrotron process. And you can see how artist's impression of the accretion disk and the black hole at the center and this network of intertwined electric and magnetic fields that accelerates charged particles in the environs of the black hole and produces this enormous jet which radiates. So this synchrotron emission process, for those of you that don't dabble in physics very much, it's a relativistic version of the gyrocyclotron emission process, and it occurs when the particles are moving along the magnetic field lines in helical orbits with relativistic speeds, very close to the speed of light. And what that does, the relativistic effect, actually concentrates the normal dipolar radiation into a fine-ish cone which is aligned along the magnetic field. You can tell what the emission process is because, of course, the other big emission process in stars and other nebulae is thermal emission. But you can tell if you're dealing with a synchrotron emission because the signals are polarized, whereas from thermal source, they're unpolarized. Now, the spectrum, essentially, it falls with frequency, and you can talk about the signal strength being related to frequency by a spectral index. And if you plot that on a log-log, you can see that for this source, it's virtually a straight line over many orders of frequency. And the spectral index is 0.79. Now, why that's important is because the signal's falling with frequency. So ideally, you want to go down to 100 megs or 144 or somewhere close, because you're gaining quite a lot in signal strength. But for a given size of antenna, the antenna gains are low at that frequency unless you've got a lot of real estate and are prepared to build a really big array, which I know some of you guys have got. So the best frequency for detection is quite a complex issue because you've got a trade-off between the spectrum of the source and the gain of the antenna and the cost for a given size. This shows some spectra of sources: Cassiopeia, Cygnus, Virgo, and Hercules. And you can see there are sort of orders of magnitude difference between these sources. The expected signal strength at 408 megahertz from Virgo is about 560 Janskis. And if you're not familiar with a Jansky, it's 10 to the minus 26 watts per meter squared per hertz. So we're going to go for this one at 408, which is giving us about 560 Janskis. So choosing frequency and the antenna type, I would like to have used a couple of dishes at nearly 1420, because normally I'm looking at hydrogen line at 1420. But I only had one dish. I've got another one now, but this was a measurement some 4 years ago. So what I opted for were really easy-to-build low-cost Yagis at 408. And I chose the Society of Amateur Radio Astronomers design of a Quagi at 408. And it's a 15-element device. That's the predicted polar pattern. And I built 4 of those. The single Yagi has got about a 33-degree half-power beam width, and the side lobes are about 19 dB down. So it's relatively clean for a cheap and dirty antenna. Stacking 2 of them 1.2 meters apart after quite a lot of experimentation, looking for the best compromise between gain and side lobe levels. I came up with 1.2 meters, and that's giving me 17 degrees and 14 dB down side lobes, which on a polar plot looks like that. And that's one of those stacked Yagis on a test stand with measuring polar diagrams. So the antenna preamp was off the shelf. Let's not worry about the noise figure after this morning. It's got some noise figure, that you can buy for a couple of $100, exactly what it is. And it's followed up with a mini circuits standard line driver amplifier. And the whole thing's packaged onto a heat sink. And there are the two amplifiers are bolted to the heat sink, and there's some temperature control electronics and stuff in amongst it, with a heat exchanger and a fan. And the whole thing is run as a temperature-controlled head amplifier. And it's located inside the inevitable plastic box in between the two Yagis. The gain is about 44 dB, and that's plenty enough to drive 20 or 30 meters of reasonable coax to the receiver. So that's where I'm using it in that band there. 406, 408, of course, is a radio astronomy quiet frequencies. So I bolted my old ICOM together into the system and found very rapidly that it was all over the place with gain and noise. So that had to be modified with an active temperature control loop, which worked. And the temperature control unit controls both the temperature of the receiver and the head amplifiers. And typically, it uses Peltier coolers, that's standard technique. And I can hold the head amplifiers to about plus or minus 0.2 degrees C for more than a 10-degree variation in ambient temperature. And that's necessary to get any kind of stable signal over many, many hours. If I was doing it today, I would throw the ICOM away and I'd use one of Howard's magic devices, the FunCube dongle. And I actually posted an article about using that for radio astronomy, which a lot of people emailed back and rushed out and bought them. And that's what I'd use today. In fact, I used it to get this transit scan of the galactic plane, showing that you've got really quite good signal-to-noise. And I found that the FunCube was infinitely more stable after 35 to 40 minutes warm-up than the ICOM. It's actually a pretty good piece of kit. It's nice and stable with frequency and temperature. After about 35 minutes, there's quite a bit of drift before. But that's what I'm intending to use in the next version of the interferometer. The principles of interferometry are well known. It's just a coherent combination of signals from antennas spaced at a distance. And what it gives you is a set of interference fringes or beams where the width of each beam is far less than that of a single antenna. And of course, the resolution depends on the baseline that you choose. And it's interesting that almost all high-resolution radio telescopes in the world now are interferometric. And of course, when the great SKA project lifts off, it will be a continental-wide, fantastic radio telescope based on, I don't know, hundreds and hundreds of antennas located in Africa, and a second set, but at a different frequency, in Australia. So interferometry is the way it works now. This is very much an amateur version, but it shows what you can do with kit that you guys almost certainly already have. So there are my two interferometer arms. So I'm about 0.74 meters wavelength, and they're all mounted greater than 2 lambda off the ground, so that I maintain reasonably sensible polar diagrams. 30 meters separation, which is giving me a fringe period of about 5.6 minutes as the source transits across the sky as the Earth rotates. Now, that's the interferometer pattern, and to get that, I simply pointed the thing at the Crab Nebula, which is a supernova remnant, you probably know. And it's about 3 times the power of Virgo A, so it's a good calibration source. And you can see the interferometric pattern here over a couple of hours. If you put it over the whole day, that's the kind of coverage that you've got with this interferometer. And the one thing we don't talk about is back beams and ground noise and side lobes and electromagnetic interference and all the other horrible issues that you have to cope with. So just concentrating on the nice bit, we have a reasonably good interferometer pattern. And that's what it looks like in polar form. So back to the picture of the Virgo cluster. And remember, this is 1 degree. So as the Earth rotates and the interferometer, in essence, scans that bit of the sky, what we get are a set of beams, something like that, with the output fringe doing something like that with a period of 5.6 minutes. That's actually derived from the calibration from the Taurus A, the Crab Nebula. Now, how do we navigate the sky to set up the measurement? There's a really nice piece of software by Jim Sky in Hawaii called Radio Eyes. I don't know whether you've come across it. And it has an all-sky radio map, which is produced by professional radio astronomers from all over the world, bolted together at 408 megahertz, which is the frequency I was working at. It's also got a 1400 meg map, but only for the northern hemisphere. So we can find the location and set the antennas for a transit. We need to ensure a high beam elevation to avoid ground noise. And actually, for this measurement, it was a 50 degrees elevation. And the thing has to be stable over at least 5 hours either side of the transit, which is where the temperature control comes in. So this is what the screen looks like for Radio Eyes. And what you have is declination up here, which is celestial equatorial coordinates, and right ascension along here in hours. So that's the whole day unwrapped onto the screen. And this, of course, is the Milky Way. That's Cassiopeia. That's Cygnus A and Cygnus X. The galactic center is about here. That's my horizon for the particular time of this measurement. And my beam was set at 50 degrees elevation pointing due south for a transit scan. And that is, in effect, the the shape of the main beam of the interferometer. And Virgo A is there. One of the nice things about Virgo is it's actually in the near the North Galactic Pole, which means you get a relatively clear shot. Taurus A, my calibration source, is over here. So that's the source, and there's the beam, and the beam scans this way. Measurement results. These were done 4 years ago, and with the temperature control, I can actually add different days' measurements together to improve the signal-to-noise ratio. And the plot that you're going to see is the signal source, Virgo A, the output. The diffuse galactic background emission is resolved, so it doesn't show fringes. And that's one of the great things about an interferometer, is that it can pick out a point source whilst looking through this mass of stuff in the Milky Way. Because Virgo is about 10 minutes diameter and is not resolved and produces fringes. So this is the record, and it starts over here. And you can see this is the outer galactic plane. So we're looking away from the galactic center, but into the galactic plane as it rises. So you see the hump, but you also see the fringes from the point source, the Crab Nebula. And then it sweeps out towards the North Galactic Pole, and then starts to look back in towards the galactic center. And there's the thing that I'm after, Virgo A, which is just there at 13-something right ascension. And if you pull those fringes out, you can see they're reasonably clean. So that's the actual bit of record that we're interested in. And that's the expected transit time from the software. And it was within a minute or so of when it was expected. If we cut that bit out and look at it in more detail, you can see there's a total power contribution from the source there, but also the fringes. And that may be because the source is not actually a point source with a 36-minute half-power beam width, which is what the main beam width is. So we just snip that out, and there's the result. That's the interferometer signal, together with the expected transit. It's got some noise on it, obviously, because this is reasonably close to my minimum detectable signal with this cheap and cheerful interferometer. And it's about 5 times 10 to the minus 24 watts per meter squared per hertz. So low-cost, simple interferometer can be used to detect the extragalactic sources. A couple of, again, cheapish Quaggies, 408, modest temperature control, and you can detect something of a few hundred Janskis with this simple system. Improvements can be made by stacking more Quaggies, obviously getting a better antenna gain, using the SDR receiver, which is what I'm going to do, and turning the whole thing into a phase-switched interferometer. Only problem is the phase switcher is so small that there is no way I can solder it to any kind of PCB. So I'm stuck waiting for someone to help me put my digital phase switcher onto a bit of circuit board. And I need time to do it, but that's the next step for me. I'm going to build a phase-switched interferometer. So the purpose of being here really is to say that you've got all the kit, you've got all the knowledge, and why not have a go at some radio astronomy? See what you can see. That's it.